Hello and welcome to ControllersTech. Today, in part 6 of the STM32 custom bootloader series, we will look at how to flash a real OTA update directly from a server. For this demonstration, I will use a TCP server that is capable of sending the OTA file to the STM32 device over Ethernet. The application will receive the OTA file, store it in memory, set the OTA flag, and then trigger a reboot of the system. After the reboot, the bootloader will take control, flash the OTA image from the stored location, validate the application, and finally jump to the new application. The overall roadmap is quite clear, except for one important question: where will the application actually store the OTA file? To handle this storage challenge, I am going to implement two different methods, explained across two separate videos. In today's video, I will split the internal application flash into two parts. One part of the flash will be used to store the OTA file received from the TCP server, while the other part will be used for the actual application code. This approach makes the internal flash behave similar to a dual flash MCU configuration. In the next video, I will demonstrate using an external flash memory, such as the W5500 series, to store the OTA file. This external flash approach is especially useful for MCUs like the STM32F103C8, where internal flash is already very limited, and splitting it is not practical. For today's video, I will use the STM32F446, which comes with 512 kilobytes of internal flash memory, making it well suited for testing this dual flash concept. This is the updated flash structure for the STM32F446. At the beginning of the flash memory, we place the bootloader, which occupies 32 kilobytes of space. The bootloader uses sector 0 and sector 1 of the internal flash. Next, we have the application header located at an offset of 8000. The application header is 16 kilobytes in size and occupies sector 2 of the flash memory. After that, the remaining 464 kilobytes of flash memory is divided between the OTA storage area and the main application. The OTA flash region starts at an offset of C1000 and has a size of 208 kilobytes. This OTA region occupies sectors 3, 4, and 5 of the flash. Finally, we have the application region, which starts at an offset of 40,000. The application area is 256 kilobytes in size and occupies sectors 6 and 7. I could not split the remaining flash memory equally between the OTA and the application regions because of the specific flash sector layout of the STM32F446. The internal flash is organized in sectors, and we must use entire sectors, as partial sector usage is not possible. So in this layout, sectors 0 and 1 are used by the bootloader, sector 2 is reserved for the application header, sectors 3, 4, and 5 are used for OTA storage, and sectors 6 and 7 are allocated for the application. To support this new flash structure, I have also updated the flash layout.h file. This file now contains information such as the start address, maximum size, start sector, and end sector for each memory region. There are also a few small changes in the other source files, so we will replace all the previously created files to avoid any mismatch. Alright, let's begin by opening STM32 IDE. Here, I have already loaded both the application and bootloader projects from part 5. As you can see, the bootloader project still contains the OTA and image.h file that we created earlier in part 5. We will no longer need this file, but I will delete it a little later in the video. Let's begin with the application project, because this is where we need to add several new components and configurations. Open the application project in STM32CubeMX. For the network connection, I am going to use the W5500 SPI2 Ethernet module to connect the STM32 to a TCP server. I have already covered a complete series on interfacing the W5500 with STM32. You do not need to watch the entire series, but I strongly recommend watching at least the first video. That video will help you understand the basic setup and configure the connection correctly. Now, let's enable SPI1 in full duplex mode for communicating with the W5500 module. Make sure the data size is set to 8 bits and that the MSB is transmitted first. Set the SPI prescaler so that the baud rate stays close to 10 megabits per second. The pins PA5, PA6, and PA7 will be automatically configured as the SPI clock, MOSI, and MISO pins. Next, we still need to configure the chip select and reset pins for the W5500 module. Choose the required pins, configure them in output mode, and name them according to their respective functions. I am also configuring the pin PA0 as an output, which will be used to connect an LED. Now, open the GPIO configuration settings and set the output speed of the chip select pin to the highest value. That is all the configuration we need to do in STM32 CubeMX. So go ahead and generate the project. Let's now take a quick look at the hardware connection. This is how the W5500 module is connected to the STM32F446 board. I have used pins from the same side of the microcontroller to keep the wiring clean. At the top, we have the 3 SPI pins, clock, MISO, and MOSI. Below that, we have the chip select pin and the reset pin. The W5500 module is powered using the 3.3 volt supply from the STM32 board itself. That completes the hardware connection. Now that the project has been generated, open it in STM32 Cubide. Next, let's copy the updated library files into the application project and overwrite the previously created files. You can download these files from the project link provided in the description of this video. I have made some minor changes to these files, which is why I am replacing all of them here. We also need to add the W5500 library, so copy the entire folder and paste it inside the drivers directory. This folder contains the basic library files required for the W5500 module to work. I have already explained these files in detail earlier, but let's quickly go through them once again. Open the WizChip port.c file. In this file, you need to provide the SPI interface required by the W5500 module, along with the UART instance that will be used for printing log messages. I am not using DHCP in this setup, so it is defined as 0. Instead of DHCP, I have configured a static IP address for the W5500 module. The chip select and reset pins have already been defined in STM32 CubeMX, so there is nothing more to change in that section. Next, we need to add the Ethernet folder to the compiler include path. To do this, open the project properties, then go to C++ build settings, select the compiler, and open the include paths section. Add the Ethernet project folder here so that the compiler can correctly find and recognize the files inside this directory. The Ethernet folder that we added contains the files required for basic initialization of the W5500 module. As mentioned earlier, the OTA image will be downloaded from a TCP server. Because of this, the STM32 needs to work as a TCP client. The files named OTA TCP client implement the TCP client functionality on the STM32. This code allows the STM32 to connect to a TCP server, download the OTA file, and store it at the specified memory location. Let's take a moment to understand how this process works. The W5500 module supports up to 8 hardware sockets, and in this implementation, I have assigned socket 0 for the TCP client. The local port is the port number used by the client, and you can set this value to almost anything you prefer. Next, we define the OTA server IP address and port number. These values correspond to the TCP server that will send the OTA file to the STM32. In this case, I am running the TCP server on my own computer, so the IP address here is simply the IP address of my computer. Inside this file, there is a function that initializes the TCP client. This function sets up the TCP client on the STM32 by assigning the selected socket and then attempting to connect the TCP server using the details defined earlier. The next important function is OTA client task. This function is responsible for handling all TCP-related operations, which is why it must be called continuously inside an infinite loop. When the client successfully connects to the server, the socket status changes to SOC established. As soon as this happens, the function immediately sends a request message to the server. The server is designed in such a way that it only starts sending the OTA file after it receives some data from the client. So, the client first sends a small request to indicate that it is ready to receive the OTA. Once the server begins transmitting data, the client receives it using the receive function. The received data is then passed to the OTA process RX function for further processing. When this function is called for the first time, it erases the entire OTA flash region. After that, it parses the header present at the beginning of the OTA file and then starts processing the remaining data. As you may recall, the OTA file starts with firmware metadata such as the magic number, firmware size, CRC value, and version information. This function first extracts and handles that metadata. Even though the metadata is simply copied into the OTA flash area, the firmware size information is important because it helps determine whether the complete image has been received. For this reason, parsing the header at the beginning of the OTA file is mandatory. Finally, the actual data received from the server is written to the required memory location using the OTA write function. This function can be modified based on where you choose to store the OTA image. In this case, I am storing the OTA directly in the internal flash memory, so this function performs a flash write operation. The data from the server is received in bytes, but STM32 flash memory is organized in words. Because of this, I have added a new function inside the flashoperations.c file. This function first combines the received bytes into words and then writes those words into the flash memory. Here, the flash offset is set to OTA start address. This offset tells the function where the OTA image should be stored inside the flash memory. If you are storing the OTA image in an external flash device, you should set this offset to 0. Since this is a real application project, we do not want the device to stay connected to the server all the time. For that reason, I decided to implement an OTA trigger mechanism, such as pressing a button. The application will continue running its normal functionality, and only when the button is pressed will the OTA process begin. Once triggered, the application will first initialize the W5500 module and then connect to the TCP server. In a similar way, when the OTA process RX function finishes writing the complete OTA image into the specified memory location, it will call the OTA finalize function. This function disconnects the client from the server and closes the TCP socket. After that, it enables the OTA request by setting the OTA flag in the application header. Finally, it resets the MCU so that the bootloader can take control and flash the new OTA update. Now, let's see how this is implemented in the main.c file. First, include the OTA TCP client.h header file. We no longer need the application header section here, because the application is not responsible for updating the header anymore. Next, define a variable that will be used to start the OTA process, and set this variable when the button is pressed. Inside the main infinite loop, check this variable, and if it is set, start the OTA procedure. Make sure to add a small delay to avoid button debounce issues. Also remember to reset the variable after triggering the OTA, so the process does not start again unintentionally. As mentioned earlier, the OTA client task function must be called frequently inside an infinite loop. However, we should not call this function all the time, because it should only run when the STM32 is acting as a TCP client. To handle this, I have defined a variable called OTA active, which is set when the TCP client is running. This variable is cleared once the OTA image has been fully written to the target memory location. We can use this variable to control when the OTA task should execute inside the main loop. Define this variable as an external variable in the main file. Now, inside the while loop, if this variable is set, call the OTA client task function inside another infinite loop. This pauses the rest of the application and ensures that the OTA task keeps running until the entire image is stored successfully. With this, the TCP client logic is now fully integrated inside the main loop. If the OTA process is not triggered by pressing the button, the application continues to run normally. In this example, I am simply blinking a LED to represent the application, with the LED toggling every 2 seconds. That is all the code we need to add for the application logic. Since the flash layout has changed compared to the previous project, we also need to update the flash script file. We no longer need the application header section in the linker script, so you can remove it. The application flash region now starts at an offset of 40,000 and has a size of 256 kilobytes. Also remove the additional section that we added in the previous projects. That completes all the required changes in the application project, so go ahead and build the project now. Now, we will move on to modifying the Bootloader project. The Bootloader already performs most of the required tasks, so only a few small changes are needed here. First, copy the updated flash layout.h file from the application project and paste it into the Bootloader project. Then include the flash layout.h file in the Bootloader main file. Since the Bootloader will now read the OTA image directly from internal flash memory, we need to update the memory base address to the start address of the OTA region. This part of the code is responsible for reading the OTA data from the specified memory location. In the previous project, the OTA image was read from a separate header file. Now, however, the OTA image is stored directly in flash memory. So, we first update the pointer to point the new memory location. After that, we use the memcopy function to copy the required amount of data from this flash location into the buffer. That is all the modification required in the Bootloader project. All other steps in the Bootloader remain exactly the same as explained in the previous video of this series. Now, let's build the Bootloader project. The build completes successfully, and now both the application and Bootloader projects are ready to be flashed. Since the Bootloader has been updated, we should flash the Bootloader first using STM32 Cube Programmer. You can directly flash the ELF file if you do not want to manually enter the flash address. After flashing, disconnect the SD link and reset the board. Next, we will flash the application project using STM32 Cube IDE, because we need to run it at least once. Open the application project and click on Debug. Create a new debug configuration for this project. Go to the Startup tab, and under Start Address, select Specify Vector Table. Here, enter the start address of the application flash memory. Click Debug to start the debugger. The application project is now loaded successfully, so click the Run button to execute it. Now, go to the application debug folder and generate the OTA image.bin file. Next, copy the OTA server Python script into the same debug folder. Let's quickly take a look at this script. Inside the script, you can define the server IP address and port number. This server looks for the OTA image.bin file in the current working directory, so make sure the file is present there. As mentioned earlier, the server waits until it receives some data from the client. Once the server receives this data, it begins transmitting the OTA file to the STM32. Now, let's run this script. Here, you can see the logs showing that the server is listening for incoming connections. Let's also check the logs on the serial console. You can see that the application is running normally, with the LED blinking every 2 seconds. Now, I am going to press the button to trigger the OTA update. You can see that the process has started with the initialization of the module. The IP address has been assigned to the module, and it is now trying to connect to the server. Alright, the entire process has completed successfully, so let's quickly understand what happened. First, the server was waiting and listening for incoming connections. When the STM32 acted as a client, it connected to the server. The client then sent a request to the server, and in this case, any data sent by the client is sufficient. After receiving the request, the server started transmitting the OTA file, which has a size of 28,164 bytes. Once the OTA file was fully transmitted, the server closed the connection. On the client side, a total of 28,164 bytes were received from the server. Out of these, the actual firmware size is 28,148 bytes, and the remaining 16 bytes are used for the firmware metadata. After the firmware was received and stored, the system was reset. The bootloader then ran, flashed the OTA update, and finally jumped to the application. The application is now running correctly. At this point, we have a complete structure in place, and manual flashing is no longer required. Let's test the process one more time to confirm everything is working as expected. I have prepared a new application that blinks the LED every 100 milliseconds. First, let's build this new application. Since this is an update, we will also modify the Python script to increment the application version. Now, generate the OTA image.bin file for this updated application. After that, start the server so it can push the update to the connected client. Now, press the button on the STM32 board to trigger the OTA process. The process completes successfully, the bootloader flashes the OTA update, and then jumps to the application. You can see that the LED is now blinking every 100 milliseconds. The bootloader also writes the application header, which allows us to verify the application version using STM32 Cube Programmer. Here, read the application header sector, and you can see that the application version is 5. This matches the version number that we updated earlier in the Python script. So, we have successfully flashed an OTA update directly from the TCP server. The entire process is now almost fully automated. There is no longer any need to manually insert the CRC or firmware size into the application, or copy a generated OTA header file into the bootloader. The application downloads the update, stores it in flash memory, and then reboots. The bootloader verifies the update, flashes it, validates the new application, and jumps to it. The only remaining task is to define how the OTA process should be triggered. In this video, I used a button as the trigger, but you can implement any other trigger mechanism based on your requirements. In the next video of this series, I will return to the STM32F103C8. There, we will implement the same OTA process using an external flash memory, such as a W5500 device. The OTA update will be downloaded and stored in the external flash, and then flashed using the bootloader. That brings us to the end of this video. I hope everything was explained clearly and was easy to follow. You can download all the files used in this video from the article linked in the description below. Feel free to leave a comment if you have any questions or doubts. Keep watching, and have a great day ahead.